Alright, in this video I'm going to be showing you a few of the data visualization, interpolation, and analysis features that are available to you in ParaView. ParaView is a really powerful tool. I really like using it, and we're only just going to scratch the surface of some of the capabilities that ParaView has, but I'm hoping to show you a couple things that could be useful for you for your panel method. So to bring in one of your surface mesh results, we're going to click on this open icon. You're going to navigate to where your results are. I'm going to pull open just a NACA wing, and then once it's loaded in, you're going to hit apply right here, and that will actually render that mesh as you pulled it in. Now you can see it's colored, and this color bar over here is telling us it's colored according to mu. Well, that's at the doublet strength. If you want to change that, you go up here and you click on mu, and it'll bring up this drop down that shows you all of the variables that you have exported along with your VTK. So in your export VTK, you added in those results dictionaries. That's where these will show up in ParaView. So we can switch them. We can look at CP incompressible. We can look at the surface velocity, whatever those we like. These icons here on the left simply indicate whether it's cell-based data or point-based data. So mu and Vu are point-based data. Cell-based data means it's constant over each panel, and that's what you're going to be dealing with in your panel method, unless you decide to take things a little bit further. But we're going to stick with that for now. So let's look at CP incompressible. This is our incompressible pressure coefficient, and I got this out of my Fortran panel code mock line. But you can see we've got a nice distribution predicted here. We've got a stagnation region underneath the leading edge. We've got that suction region over the leading edge. Really, this looks quite good. But if we wanted to, say, compare this to experimental data, then we need to be able to do that in terms of like chord-wise slices. You know, if you look at the literature, they're always reporting, okay, this is the pressure contour at a given y coordinate. And so we're going to show how to do that in ParaView. First thing you're going to do is you're going to go up to the top, click on Filters, come down, click on Alphabetical, and then under Alphabetical, you're going to click on Cell Data to Point Data. And what Cell Data to Point Data does is it takes that cell-based data and it does some fancy averaging and mixing on it to take that out to the vertices instead of being constant over the cells. You'll hit Apply, and you'll notice that our results are now a little smoother than they were before. There's not that hard break in between panels anymore. Once you've run the cell data to point data filter, you're going to go up again to Filters, click on Alphabetical, and go over to Plot on Intersection Curves. What this will do is it'll draw a slice through your mesh, and wherever your mesh intersects that slice, it'll plot the data on that. You'll want to make sure that you've got slice type is plane. You can do other types of slices, but we're going to deal with plain slice for now. And since I want to do a chord-wise slice, I'm going to set that the normal vector of that plane is just the y direction. So now this red box we can see is lined up with the chord-wise direction. And then you can set the origin either by clicking on that arrow and dragging it, or you can set it here manually, however you would like to do that. I like to do it over here just because you can be exact. So now we've got our plane, and don't worry about it only partially intersecting the wing. It'll expand that to encompass the entire mesh. So let's hit Apply, and now we've opened a whole new view. We've still got our mesh over here, but over here is where we're actually viewing that intersection data. Now this all looks a little nonsensical. There's a lot going on here, and I'll explain what exactly is happening. If you go over here to the left and scroll down, attribute type, we need to make sure that that's point data. ParaView doesn't do a great job of plotting cell data on intersection curves, so that's why we did the whole cell data to point data thing. And then here under X array name, instead of arc length, we need to set that to be points X. So we can see that now, that looks much better. What that did is it said, rather than having the x-axis of this graph be the arc length along the slice that you've taken, have it just be the x-coordinate of the points on the mesh, which obviously makes a lot more sense for what we're going for here. And then, again, we've got a lot going on here. This kind of looks like our pressure coefficient, but that's actually our V magnitude. What ho, the two are tied. But let's just look at pressure coefficient. So over here, you can see that we've got a whole bunch of these variables are selected. And let's go ahead and unselect everything except for the pressure coefficient. And voila! There is our pressure coefficient right there. And you can see, you know, that looks exactly like what we would looks exactly like what we would have gotten out of, say, our Vortex panel code, or something like that. And then you can scroll down further, and you can mess with some of the aspects of the graph here. But that's all we need for now. This looks great and all, and you can make some comparisons this way, but it would be nice if we were able to take this and plot it in our own software. And then we could add in extra data points from experimental data or whatever, or from an analytic distribution that we have. So what you can do here is you can click on Save Data, this folder with the green arrow. You're going to click there, and just navigate to wherever you want to save things. You'll probably want to save it as a CSV file. CSV files are just easy to parse using Python. You can also pull them up in Excel or whatever you like. And we'll call this pressure slice.csv. We'll hit OK. Precision, you can specify how many decimals of precision you want. Since this is just for plotting, we're going to stick with 5 decimal places. It's not terribly critical. And we want our point data. Click OK. And then let's go ahead and pull up that data. Go into where we've stored that. This will take a moment to load, but so I'm just pulling it up in OpenOffice here. But you can see it's put out everything from that mesh along that slice. So we've got our pressure coefficient, then we've got our point coordinates. So we could go ahead and insert a chart here of pressure coefficient versus that 0 coordinate. That's our x coordinate. And then you could add extra columns here to represent, like I said, experimental data, or maybe an analytic result that you have, or data from your Vortex panel method. And you can make a comparison that way. That's all I'll show you there as far as slicing goes. Like I said, ParaView is really, really powerful, and there's a lot that we're not going to get into. But I will show you another feature that you can use, and maybe you might find this useful. If you can export from your code a CSV file of data at a whole bunch of points, then you could open that in ParaView as well. So say you got, say you wanted to calculate the flow field around a sphere, you could distribute a whole bunch of points in x, y, z around that sphere, and then you could calculate the velocity and potential at each one of those points, and you could write that out to a CSV file. So in a CSV file, you've just got the first line is your headers, your variable names, and each one of those is separated by a comma, and then you've got each one of your columns separated by a comma. So here x, these are my x coordinates, y, these are my y coordinates, z, these are my z coordinates. And again, this is a slice that I created using mockline. What we can do is we can actually render that in ParaView. You know, a CSV file isn't very great for us to look at, but we can do some pretty cool things with it. So we're going to open slice.csv. Yep, so you want the CSV reader. Click OK, and just hit apply. And that will pull all this stuff up in a table. And you can just look at this and verify that they've correctly parsed your CSV. Everything's looking good, so we can actually close that. We don't need that anymore. You're going to go up to filters again, and you're going to click on alphabetical, and you're going to click on table to points. What this will do is it'll take your tabulated data, and you can tell it, okay, I want my x coordinate to be specified by this column in the CSV file. So I've got an x column for my x coordinate, so I'm going to select x for that. Y column is y, obviously, and z column is z. So now I've told it, okay, these are the coordinates of the points. Let's go ahead and apply it. And look at that. Now I just have a slice in the xz plane, and so that's why there we go. That's what I wanted. I just have a slice in the xz plane, and so that's why it looks, it's kind of locked the rendering to be normal to the y plane, but that's okay. And again, we can go up here and we can look at all the point data tied to this one. This is on a supersonic airfoil, so you get really cool looking perturbation potentials coming off of this. I love supersonic results. They just look so cool. Anyway, but it's kind of annoying to have this be points, right? So what we can do is we can go up to filters and we can turn this into a surface using Delaunay 2D filter. So click on alphabetical and go to Delaunay 2D. And you'll want to make sure that here under projection plane mode, instead of XY plane, just click best fitting plane. Now if you had a three-dimensional set of data, if you had points distributed out throughout space, rather than clicking on Delaunay 2D, you would click on Delaunay 3D right here. But they do essentially the same thing. Click apply, and it's going to run through. It's going to run an algorithm whereby it creates a triangulated mesh off of all these points, and then it's going to use that point data and linear interpolate across each one of those cells that it creates, and you get a result that looks like this. So that's much, much nicer to look at. Now we have an actual surface, and we can see what's across it. Another really powerful tool that we can now apply is, I've got here, phi is my velocity potential. And so what I can do is I can come into filters, and I'm going to say, well, I've got my velocity potential. Let's find out what the velocity is. Well, what is the velocity in terms of the velocity potential? It's the gradient. So let's go into filters, alphabetical, and click on gradient. We're going to say I want to take the gradient of phi, and I'm going to call the resultant array v. V is my velocity. I'm going to click apply, and it's still coloring in terms of phi. Gradient inherits all the data attributes from the previous class. So we'll go up here, and rather than selecting phi, we're going to select v. Now it's a little off. This is because of the particular boundary condition formulation I'm using. We get sharp jumps in pressure in between, or sorry, not sharp jumps in pressure. So we get sharp jumps in velocity in between the inside and the outside of the configuration. So rather than doing automatic rescaling, I'm going to update the range myself. I know my free stream velocity is 1, so I'm going to go from 0.87 to about 1.25. I'm going to rescale that. And there we go. So we can see here at the leading edge and the trailing edge. Actually, this isn't a supersonic result. I apologize. This is a subsonic one. It's just on the supersonic airfoil. At the leading edge and the trailing edge, we've got really low velocity. We've got close to our stagnation points. At the upper and then at the points of maximum thickness, we've got really large velocities. Those are our points of minimum pressure. Anyway, there's a lot you can do from here to fiddle around with things. You can apply calculators. You could even go ahead and use this calculator to calculate the pressure coefficient if you like, but I won't get into that. Like I said, there is tons and tons of stuff that you can do with ParaView, and there's lots of tutorials online, but I wanted to give you just a basic introduction to say these are some features that I think you'll find useful for your panel method project.